Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 5 Part C. And so there's this whole paragraph here, but basically what we're doing is a giant mass balance on this distillation system, and so we're going to divide it up into 3 columns. So we have this one here, the second one here, and then we're going to combine these two into one. So if we come over here, we can draw that out a little bit more clearly. So this is our reactor. Then we have D1, and then we have over here AZ. So as far as the inputs for reactor, the reactor R is we have our water. We also have our alkene, and then the outflow is what we'll call D1F, and then that also is an inflow for D1. And then D1 has an outflow of D1D. It also has an outflow here. Get rid of this. That recycles water. And this is D1B. And then for AZ, we have our output of ether product. And we have our output of alcohol product. And then finally, we have one last outflow that also recycles water that we'll call decanter W. So the first thing that we want to do is figure out how many equations we are going to need, and then how many variables we're going to need to define. So as far as the equation go, we are going to have 4 equations for each of these columns, since there are 4 components associated with this scenario. So if we have 4 equations and 3 columns, that's 12 equations total. And then we also have our equilibrium equations, and so these are associated with the value K. So this is D1K, which is equal to the mole fractions for D, or D1D, and the mole fractions for D1B. And this was given to us. So we know that this is going to be 100, 10, 5, and 0.2. But with that, we have another 4 equations, giving us a total of 16 equations. And then for variables, there are 4 molar flow rates associated with each stream. And we see that we have 1, 2, 3, 4, 5, 6, 7, 8 streams in this system. So we have 4 times 8, which gives us 32 variables. And then if we just take 32 minus 16, we get 18 variables that we need to specify. So this problem is just a more complex, more detailed version of what we just got done doing for Part B. So we can actually go ahead and use some of the code that we had used for Part B. The first thing that we want to do here, though, is create a dictionary, and we'll just call it E. And so we just have to go through input E dot in front of all of these to add them to our dictionary. Okay. And then we want to add a couple new libraries. So we have import jax and then import jax.numpy as JNP. Enter on all of those. And then we want to get rid of that, and we can define a new function that we'll call equations2 that this time takes in a dictionary and instead of a vector. And the benefit of this is that now we don't have to rewrite our function every time we change what is known versus unknown. We can just come up here and change that within our dictionary instead. And so what we want to do is write out our equations. So if we start with our reactor, we have our reactor feed. And so the reactor feed is the same as it was for part B, so we can just steal those. So we have to put D dot in front of these to make it a part of our new dictionary. And then these are now not the only feeds that are going into the reactor. We also have the D1B and our decanter water. So we have D1B times D1BX plus dot decanter water times D dot decanter water X. Our reactions are exactly the same. So again, we can just come over here and steal those, being sure to add D dot in front of all of those. And then finally, we have our reactor products. And this time, instead of the ether and the alcohol products, we have D1F as our output. So that is just D1F times D1FX. That. Okay. And now we are ready to do our reactor balance. And so we just have our reactor feed plus, not spelled today, here we go. Reactor feed plus our reactions minus our reactor products. And then now we can move on to our E1 balance. And so for that, we have our input being the same as the output for the reactor. And then our outputs are D1B, so we can just steal that. And then it is also D1D times D1Y. Next up is our AZ balance. So now this has this output here as an input, and then it also has this decanter water as an output, as well as what we had as outputs for the. Now we have to add the dot in front of all of those. Change this sign here to a negative sign. There we have our mass balances. So there are two more things that we need to take into consideration before we can return our equation. So the first is the water alkene reactor feed ratio. So this is just all the water feeds, so the main one that we have talked about since part B, as well as the decanter water and the D1B water. So this is just the water being recycled. All of that divided by the alkene feed. So, oops, this is actually the name that we want. Here is, we'll call it water constraint. So we will have this water feed plus canter stream plus 1B over dot alkene feed, and now it's minus the go. And then it looks like we did forget one balance. We need to do our vapor liquid equilibrium balance that's associated with D1. And for this, we had what we had written down here. So it is just d dot d1 dy over d1 dx. And that is just minus d dot d1. Perfect. And now we have everything that we need. So we are going to combine all of these. So we're going to go JNP dot concatenate. And so we have our reactor balance. We have our D1 balance, AZ balance, D1 LE, and then we have to do JNP dot at least 1B, and that is for our water constraint. Okay, so now that we have our function, we're going to work backwards a little bit and figure out what we need to specify and what is known. So first we have here what our initial guesses were for part B, but now that we have a dictionary, we're going to pull on some of the functions that we have here from our GitHub. So for this, we're going to use range. So we have range and then our initial guess. So for this, we're going to do E dot alkene F divided by 2 as our guess. our lower bound is 0, and then our upper bound is just alkene F. For our extent of reaction 2, we're going to do E dot alkene F divided by 4, with our lower bound being 0 and our upper bound being E dot alkene F divided by 2. For our ether product and alcohol product, we are going to keep what our guesses were and just add some bounds. So we have bound of 0 and then E dot alkene dot F divided by 2. And then for this one, we have range 50, 0 as our lower bound, and E dot alkene F as our upper bound. Okay, so here we have 4 equations. Just to keep track of how many we've done, or I guess not equations, we have 4 unknowns. So next, I'm just kind of going to move through this system. So I'm going to first start with this D1F. So we've already gone through the alkene and the water feed. Okay, so we have E dot D1F. And so we have to have a range for this. So we have range. We're going to do E dot WAF is. So our feed in is always going to be at least this ratio times the alkene feed. So that's going to be our guess. Our lower bound is going to be 0, and our upper bound is going to be 2 times what our initial guess was. And then just before I forget, I'm going to define our ratio. And this was given to us to be 12. Okay, and next we have our D1X, so our composition. So this time we're going to use comp. And we're just going to take some guesses at what we think this composition is going to be. So we can do, for this we can assume that it's going to be mostly water, so maybe 0.01, 0.03, 0.06, which give us 90% water. And so now this gave us another 4 unknowns. Moving on, we have D1B, so we're just going to do the same thing. For this one, I'm just going to take this range and paste it here. We're just going to divide that by 2 maybe. And then for our composition, we're going to guess that maybe it's all pretty even, but we should have used up most of that alkene by now. Okay, so that's another 4 unknowns there. And then we can look at D1B. So actually we're just gonna do this and say that it's 50-50 there. And we can do E dot D1X. And for this one, our composition, we're going to say 0.1, 0.002, point. Sure. These are all just kind of random guesses. As long as they're reasonable, it doesn't really matter what you put in. And this gave us another 4 unknowns. And so right now we are up to 16, so we only have 1 left. So now we're moving on to our decanter water. And so we can't just repeat the same process that we just did, because that would give us 4 more unknowns, and that would be over our limit. So we are going to just do this first one. And actually, we're just gonna copy paste from up here. And then we are going to say that we measured the composition, or the composition is known, or somehow it's known. So we have that, and then we just do np dot array. We have point a very, very, very small amount of our alkene. Let's see. How much of this other stuff can we say we have? We want it to be mostly water, so if we say that it's, we say that it's 90% water, we say 0. Maybe I'll do this one here. Give us very small values, and say here that we had 1. Okay, so if I could stop struggling to do math, this would be 80%. There we go. And so now this gave us 1 unknown. And so there are our 17 unknowns, or variables. And the last thing that we need to do is remember that we have dot d1k, and that was given to us. So we have np dot array, and our numbers were 110, 5, 0.2. And that should be everything, but I guess we will find out here in a second. So now what we want to do is use this. Oops, what did I do? I don't know why it doesn't want to do that. Okay, so this key error should just be because I forgot to do that. And I forgot to do it here, here, anytime that I really use that word, I guess. There we go. Okay, so now what we want to do is come up here and use this d2nt. And so this returns 5 things. So we have x naught, which is our initial guess. It gives us x to nt. It gives us wrap. It gives us x to unknown and constant. constant, so now we use d to n t e. And so for us, what we really are going to use is this x naught, which is our initial guesses, this wrap, which is going to wrap our function, basically giving out a new function that allows us to put our equation into our root solver. And then this unknown just so that we can see our results more easily. So we have that, and then we want to do solution is equal to root. So I forgot a step. We want to first wrap our equation, our function. So we have wrapped equations 2 is equal to wrap equations 2. And so now that we have that function, we can put it here into our root solver. And we have our initial guess, which is x naught, and then we want to do Jack is equal to Jack's dot Jacobian, and then we just put our function in here, equations 2, and then we can print this just to make sure that it's working. Okay, and then we can go ahead and do this x2 unknown. I'm going to put sol.x there, and then dot underscore as. Now we should be able to see all of our unknowns here and what their values are. Okay, so I had that whole struggle with making reasonable guesses, and then I watched the video back and realized that my answers were still wrong. So I think what I did was I just mistyped and forgot a 0 right there. So hopefully, as we go through, that should correct the problem. Let's see. And that is looking much better. And there are the correct results for all of our unknown variables.